Well, time to do some more practice with partial fractions because that's going to be a really important tool. It's the algebra tool of choice for pulling things apart, especially when you have things downstairs in your denominator. And when you're using the Laplace transform, that's what happens. So we got to do it. We got to get that practice in. So we're going to do some more problems, also do a problem involving systems all the way to the end so that we can be like, yes, we've practiced. So let's do it. Yeah! Our first problem we're going to look at. Solve x triple prime, 3 derivatives, plus x double prime minus 6x prime equals 0, with x of 0 equals 0, x prime is 0, and x double prime is 0, both being 15. So when you see this lineup, they're all equal to 15. And we're like, wow, this is a fantastic differential equation. It's our favorite kind of differential equation. Constant coefficient, homogeneous, life is good. So it makes us want to sing, girl, you are to me all that a differential equation should be, and we dedicate ourselves to you always. Of course, you're thinking, wait a second, we don't need to do Laplace transforms to solve this, do we? No, of course we don't need that. But we should practice it because, well, it's our new tool, and we're not good at it yet. So the more we practice, the better we get. And we also get to see how it works. Okay, so where do we begin? Well, the first step is always to say, take the Laplace transform of both sides. And we almost always say, jump right in and say, hey, linearity, let's just simplify that process. So in particular, we have that the Laplace transform of x triple prime plus the Laplace transform of x double prime minus 6 Laplace transform of x prime equals the Laplace transform of 0. Now the Laplace transform of 0 is 0. I mean, you'd want that to be the case. Essentially, anytime something is linear, 0 goes to 0. It's very nice that way. We like 0. 0's a friend. Now, what about these other pieces? Well, they involve the Laplace transform of derivatives. And of course, you always have your equation sheet of some kind handy. And we see, well, for x prime, it'll be s, x of s minus x0. X double prime, s squared, x of s, minus s, x of 0 minus x prime of 0. And in general, and this includes the third derivative, so for the third derivative, it would be s cubed, x of s squared, x of 0. Then it would be s, x prime is 0. And then it would be, at the end, minus x double prime is 0. Okay, so this becomes, here we go, we have our s cubed capital X. So I'm thinking of capital X as what happens when you transform little x. Okay, so s cubed capital X minus s squared times 0 minus s times x prime, 15, minus x double prime, 15. Okay, so that's the first piece. And then we say, all right, but there's more pieces. Yeah, no worries. We have lots of space left on our paper. X double prime, so plus, and I like to put parentheses. It helps remind me, hey, don't forget to put parentheses here. So s squared x minus s, x of 0, 0. Oh, it's really nice that we have a 0 there. That's lovely. Wouldn't it be lovely? Minus x prime is 0, 15. Good. And now, one more term on the left-hand side anyways. And that term. So minus 6 parentheses. Remember, parentheses help remind us that that minus 6 will distribute. So make it a good habit to be like, I'm going to use parentheses because that's going to help me save points. And we want to get all the points, all of them. All right, so that would be s x minus x of 0. Good. Okay. Whew. And finally, of course, we set this equal to the other side, which is 0. Okay, so our first step is done. We took the Laplace transform of both sides. Now for our next step is we're going to channel our hunter-gatherer. And namely, we're going to hunt for things with x, we're going to gather them together. We're going to hunt for things without x, we're going to gather them together. Now, what has an x? Well, there's 3 terms that have x. So we have an s cubed plus s squared minus 6s times capital X equals, and we're going to put everything else on the other side, we have a 15s. Okay, I'm going to switch colors here just so to emphasize 15s, great. And then we have a minus 15 and a minus 15, so those are going to give us minus 30. Well, I should also say we have a 0 there, but that won't make a big difference. So 15s plus 30. And, well, there's a 0 there, but again, that doesn't make a difference. All right, so we've gathered, and now we're like, okay, wonderful. So we can solve for x. Well, before we finish off, let's just clean up a little bit. This part right here, we can clean that up. Everything has an s, so let's factor that out. S squared plus s minus 6. And we say, well, does that factor? Well, I'll tell you, surprisingly often, these problems factor. In real life, they wouldn't factor, but that's okay. In real life, we probably have a computer. So, we all make compromises. So what do we need? We need 2 numbers that multiply to negative 6, but add to positive 1. Well, 2 numbers that do that would be plus 3 and minus 2. You can check. We get the s squared minus 2s plus 3s would be s, and 3 times minus 2 is minus 6. So that allows us to say the following, namely that x is equal to 15s plus 30. Divide that by s times s plus 3 times s minus 2. All right. Whew. Good. Now, we're ready to transition to the next phase of the problem. We've already started the algebra phase. The algebra phase starts as soon as you do simplification. And that means solving for x is simplifying. And remember, what's the goal for algebra? Algebra says, let me write this in a simpler way. That's it. That's what algebra is all about. It's saying, hey, I'm going to help you solve it, but the way I help you solve things is I simplify things, and I do it in a series of steps. And at the very end is the answer. So math is a lot about, can you simplify things to get it down to what's the real essence? What's the key here that we see? Okay, so we're going to switch now and say, all right, our new problem is a partial fractions problem. So, namely, this 15s plus 30 over s times s plus 3 times s minus 2 is going to look like, well, we have 3 parts. So there's something over s plus something over s plus 3 plus something over s minus 2. Clear out your denominators. And the way we do that is we say, hey, do these terms have anything in common? The denominators, well, yeah, of course they do. What you do is you look at this part, say, I'm going to multiply everything by what I see there, s plus 3, s minus 2. And what we end up with is we end up with the following. We say, okay, we have 15 times s plus 30 is equal to a. Now here, the s terms cancel, so it would be s plus 3 times s minus 2. Then b, the s plus 3 terms cancel, so it would be b times s minus 2. And for c, the s minus 2 terms cancel, so we get c times s plus 3. And we're in our sort of happy place because this problem is ideal for pick a number and evaluate. So what do I mean by that? Well, I mean, make good choices, right? So for instance, let's make the choice s equals 0. If we do that, we're going to get 30 on the left-hand side, and boom, boom, the b and the c term go away, so we get equals to a times 3 times negative 2. Well, minus 6a equals 30, a equals negative 5. Wonderful. All right, what about, let's say, s equals negative 3? Now you might say, what? Why are you going in that order? Well, 0 is here, negative 3 is there, 2 is there. So I'm just working my way, A, B, C. So negative 3, all right. Well, okay, we've got to think a little bit here. Negative 45 plus 30 is negative 15. Gone, gone. What's left? Well, we get b times negative 3 times negative 5. Okay, well, negative 3 times negative 5 is a plus 15. Negative 15 divided by 15, well, that says b is negative 1. Okay, now our last one. That it would be for s equals 2. What do we get? Well, we get 30 plus 30 makes 60. Gone, gone. C times 2 times 5. Which tells us C equals, well, 6. Great. So, we're in the home stretch. Why? Well, because we know this is the Laplace transform of our answer. And now we found a better way to write our answer, or rather I should say the Laplace transform of our answer. So we can say, hey, the answer will be the inverse Laplace transform of negative 5 times 1 over s, then minus 1 times 1 over s plus 3, and then 6, 1 over s minus 2. And these are things that we know. So for example, 1 over s, that's near the top of our list. In fact, it literally is the very first thing on this list. It's 1. And these other things, if I say 1 over s minus something, that's an exponential, e to the ct. So we end up with here negative 5. Then here we'll have a minus. Now this is s plus 3, which is s subtract negative 3. So that's going to be a e to the minus 3t. And here we'll get plus 6. And then we're going to get e to the 2t. And we're done. That's it. Remember that when we're doing this problem, that our initial conditions don't happen at the start. Don't happen at the end. They happen right at the start. It's kind of reverse process that way. It's one of the cool things about Laplace transform is oftentimes you're like, I got to wait till the end to sort of like make things work correctly. And Laplace transform says, no, just give me the information at the start and I'll make sure that you get the right thing at the end. Now you might say, are there some things we could do to check our answer? Well, one thing you could do is spot check some initial conditions. So for example, when you plug in 0, do you get 0? Well, you get minus 5 minus 1 plus 6, which is 0. That's a good sign. We can even quickly check the derivative, right? So here, that would go away. We get a plus 3, because that minus 3 would come down. And we get a plus 12, which is 15. Yeah, that's pretty good. If we were really bold, we could even take the second derivative. Here, a minus 3 would come down twice, so you end up with minus 9 here. Here, a 2 would come down twice, so you end up with a plus 24. And 24 minus 9 is also 15. It works! It's the right answer! The crowd's going wild! Oh my goodness! Wow! It's really fun when it works, isn't it? I recommend it. When possible, make sure that your problems work out nicely. All right, well, that was a good one, but I'm sure we have some more interesting ones coming as well. In this problem, we don't have to solve a differential equation. We need to find the inverse Laplace of this expression. s to the fourth minus 3s cubed minus 2s squared plus 5s plus 8 over s minus 2 to the fifth. Now you might look at this and say, like, that looks scary because we're going to have to solve for 5 constants. Now you might want to say, wait, how do you know we're going to have to solve for 5 constants? We haven't even done anything. Well, there's a trick actually. You look at your denominator and you say, what's the degree downstairs? You say, oh, well, it's a 5th degree. And I say, that's how you know. So whatever the degree is downstairs, that's how many constants you get to solve for. So they're like, all right. And, well, what do? The good news is our denominator's already been factored for us. So that saves us a step. So what do we have? Well, we say, okay, since it's s minus 2 to the fifth, what it means is we got to work our way up. So we have s minus 2 squared, s minus 3 cubed, so forth and so on, all the way up. So in particular, we have the following. This is going to be s to the fourth minus 3s cubed minus 2s squared plus 5s plus 8, just copying it down, haven't done anything yet, over s minus 2 to the fifth equals, okay, we're going to have something a over s minus 2, b over s minus 2 squared, c over s minus 2 cubed, d over s minus 2 to the fourth, e over s minus 2 to the fifth. Ah, wow. Okay, well, yeah, that's just how the rule goes. So we now know our rule. Now at this point, what comes next? Because we're not going to do anything with inverse Laplace until we get this settled. So the next thing for us to do is to clear out our denominator. So we're going to multiply everything here. Both sides, everything is being multiplied by our s minus 2 to the fifth. Okay, so doing that, we get s to the fourth minus 3s cubed minus 2s squared plus 5s plus 8 is equal to a plus b, a, I thought I was at that end. No, I'm at this end, times s minus 2 to the fourth, to the fourth, yep, that's right, plus b, s minus 2 to the third, plus c, s minus 2 squared, plus d, s minus 2, plus e. All right, there we go. Wonderful. Great. So now what do we do? Well, we look at this and say, we have a good choice, right? Yeah, we have a wonderful choice. Namely, plug in s equals 2. We'll get 16 minus 48 minus 8 plus 10 plus 8 equals 0, 0, 0, 0, e. All right, so there we go. We plugged in s equals 2. And, well, if we do that, okay, we can see that here, like the 8s cancel pretty quickly. You have a 16 plus 10, which is a 26. And then you subtract 48. So that would say that e would have to be equal to a minus 20. Oh, wait a second. Why did I say 48? Because it is 48. That's why I said it. Right? No, wait. 2 cubed is 8. 8 times 3 is 24. That's what happens when you're not paying attention. Okay, so 16 plus 10 is 26. 26 subtract 24 is a plus 2. There we go. Yeah. Double check your work. Right? No matter how long you've been doing math, it's really easy to get caught up in the heat of the moment and be like, So, all right. So there we go. So now we have one of our answers. And at this point, you're saying, okay, what's another good choice? And you're like, is 2 a good choice? Well, yeah, but we've already used it. And there's not another great choice in terms of knocking terms out. Now, we could start expanding do you know what s minus 2 to the fourth looks like? Well, yeah, it looks like s to the fourth. Next one, it's minus 8s cubed. And then 24s squared. Yeah, that sounds dangerous to do that. So let's not do that. So this is where we're going to use another fun fact. See, when we're solving for coefficients, the two big ones, the one that most people learn when they first see it, is set coefficients equal and solve for your constants that way. Then they say, oh, you know what, make good choices. It's wonderful advice for math, wonderful advice for life. Make good choices. The third one says, you know, really we have two polynomials which are equal, so anything you do to both sides that keeps them as equal polynomials is fair game. And then you get information from that. So let's take derivatives of both sides. Let's do it. We're allowed. Absolutely we're allowed. Okay, so when taking our derivative, we would have 4s cubed minus 9s squared minus 4s plus 5 equals 4a s minus 2 cubed plus 3b s minus 2 squared plus 2c s minus 2 plus d. Right? Because when you take s minus 2 to a power and you take that derivative, you're using the power rule. The exponent comes down, s minus 2 to 1 less, the derivative of the inside is 1. Now, look at this expression. Is there a nice choice here? Yeah, 2 again. But see now, after we've taken a derivative, we're going to get a different coefficient. So, 4 times 2 cubed, 4 times 8, 32. 9 times 2 squared, 36. That's 9 times 4. 4 times 2, 8. 5, 5. Equals 0, 0, 0. D. So what does that tell us? Well, it says D is, okay, what do we have? We have 32 plus 5 makes 37. And then here, subtract 36. That gets us down to 1. Then we subtract 8 more. So that would make us a negative 7. Okay, so there we go. That's what D is. D is negative 7. Well, fun. Now, the technique was so nice. Let's use it twice. So we're going to take another derivative because we can. So if we do that, we're going to get, well, 12s squared minus 18s minus 4 equals 12a times s minus 2 squared plus 6b times s minus 2 plus 2c. And plug in s equals 2. What do we get? 12 times 4, 48. 18 times 2, 36. And minus 4 equals 0, 0, 2c. So, what does that tell us? Well, 48 minus 40 is 8. 8 equals 2c, so c equals 4. All right. Well, we're making progress. We're chipping away from the backside. E, D, C. 2 more and we're done. So let's just keep this process up 2 more times. And let's see where we go. Okay, so we get the following. Taking our derivative again. 24s minus 18 is equal to 24a times s minus 2 plus 6b. Plug in s equals 2. And what do we get? Well, we get 48. Subtract 18 equals 0, 6b. Well, 48 subtract 18 is 30. 30 equals 6b. That says, hey, b equals 5. Oh, nice. Okay, once more. Once more to the breach, dear friends. Once more. Take one more derivative. 24 equals 24a. Oh, well, that was quick. What's our conclusion? A equals 1. All right. So, what have we done here? Well, what we've been doing is we've been taking our derivatives, which helps simplify terms. Now, I'm going to pause here and say, when is this a good idea? Basically, it's a good idea in one setting, and in one setting only. But when you're in that setting, it's a great tool to have. And the setting is when you have something that looks like this, s minus c to a power. When that's the only thing you see downstairs, just a single term, s minus c to a power, taking derivatives is super, super slick. So you say, all right, good. So what are we up to? What have we done? Well, what we've really done is found a way to rewrite this expression. So now we can say, aha, our real problem is, let's find the inverse Laplace of, now we just worked our way through here, 1 over s minus 2, and then plus 5 over s minus 2 squared, and then 4 over s minus 2 cubed, minus 7 over s minus 2 to the fourth, and then finally plus 2 over s minus 2 to the fifth. So all of our work has been to get from here to there. We're not done yet with the problem. But what we are able to say is, okay, we've now said, here's our new inverse Laplace. And we've pulled things apart to the point that we're like, I can see what to do. Okay, so now we are going to transition. So I'm going to go grab a fresh sheet of paper. I happen to have some with me. And let's just copy this problem over. So we copied the problem over. So there's our problem, copied from our previous work. And I also wrote down here something from our table. So I just took our table, and I was saying, well, where do I see something s minus something to a power? And I said, I see it here, so I've copied it down for reference. And so now we say, okay, we want to get it exactly in this form. So looking at this expression here, we can say, oh, when I look here, I can match what this should be, right? So this would correspond to n equals 0. This would correspond to n equals 1, n equals 2, n equals 3, and n equals 4. Just going by the powers here, n plus 1. So for example, if n plus 1 is 5, n should be 4. So we look at this and say, okay, so before we take the inverse Laplace, we need to make sure it looks exactly like that. So we say, okay, so what needs to be upstairs? So we come to our first term. Well, so this would be n equals 0. We want a 0 factorial. Do you remember what 0 factorial is? Have we talked about that yet? 0 factorial is 1. Now you could just say, why? Definition is one way to argue it. There's another way to think about this. And let's start with a simpler question. Suppose I have no terms and I add them together. What do you get? Well, 0, right? There's nothing there, so if you add up nothing, you get 0. Why 0? Well, 0 is a special number. It's what we call the additive identity, which means that if you add 0 to anything, you don't change anything. So that's why 0 is the default. So now, think of 0 factorial. Now, normally factorial is multiplying things. So if there's 0 factorial, we multiply nothing. So if we multiply nothing, what should we have? 1. Now, the reason is because we're talking about multiplication as our process. And for multiplication, the identity is 1. When we add, adding is our process, the identity is 0. So that's why it's 1. Empty product should be 1. Okay, so the good news is we already have a 1. So we're like, hey, life is good, nothing to see here. Now, s minus 2 squared. Well, when we have an s minus 2 squared, we need a 1 factorial upstairs. 1 factorial is 1. There's currently a 5, so we'll put the 5 in front. Come to our next term, s minus 2 cubed. We say, all right, that's n equals 2. We should have a 2 factorial upstairs. We currently have a 4. So we're going to put 2 factorial, which, well, turns out to be 2. And we say, well, we started with 4. We're using 2 upstairs. That leaves us with 2 left. Okay. Then minus, here we're going to have an s minus 2 to the 4th. Upstairs we want a 3 factorial. Okay, what should be in front? Well, we have to account for the 7, and then 3 factorial is 6. So we divide 7 over 6. Now, our last part, plus s minus 2 to the 5th. Upstairs, we want a 4 factorial. Now, 4 factorial is 24. We started with 2. We want 24. So we need to have something in front. So 4 factorial times our something gives us 2, which is 1/12. Okay, and so now we're ready. Our answer. Well, here we're just going to have t to the 0 is 1, so it's really e to the 2t. Plus 5, then we'll have t e to the 2t. Plus 2t squared e to the 2t. Minus 7 over 6 t cubed e to the 2t. Plus 1 over 12 t to the 4th e to the 2t. And that's our answer. Wow. Done. Done. Amazing. Ah, what a process. Isn't math fun? I think so. All right, well, that was good. Of course, there's always more. So let's try to look at another problem. For our last problem, let's look at this one. Use Laplace transforms to solve the following system. So now we have systems of equations. And you're like, wait, hold on. That's what we just learned. We just got out of there. Why are you taking us back? Well, we just want you to show how these tools can be used. Okay, so we have our system. We're told that x of 0 and y of 0 are both 0. That's good. And x prime is 0 and y prime is 0 are both negative 1. And we have x double prime plus 2x plus 4y equals 0, y double prime plus x plus 2y equals 0. Okay, well, let's approach our problem. What do we do? Now, the thing is, fundamentally, nothing changes. It's the same process. Now, what does change is there's a little bit more work, but that's okay. We're not shy of doing work. We just want to make sure we understand the process. Here's the basic underlying idea. Now, previously, when we've been using Laplace transform, we start with the function x, take the Laplace transform, we end up with capital X. We're going to do that again. But we're also going to have y goes to capital Y. So we keep that in mind. So capital X will be the Laplace transform of little x, and capital Y is going to be the Laplace transform of little y. So we're going to take the Laplace transform of both equations. What we're going to end up with is a pair of algebraic equations with two unknowns. So we have two equations and two unknowns. In this case, capital X and capital Y. And then we can use anything we want to solve them. We're going to use Cramer's rule. But again, we can use anything we want at that point to solve. So we start, as we often do. Let's take the Laplace transform of both these equations. So our first equation will become Laplace transform of x double prime plus 2 Laplace transform x plus 4 Laplace transform of y equals the Laplace transform of 0. Now we have our rule. Of course, keep your equation sheet handy. As the saying goes, keep your friends close and keep your equation sheet even closer. So, because, you want to make sure you have that for reference. So, what happens? Well, this term is going to become s squared capital X, how many remaining derivatives you have, that's the s to the power. So 2 derivatives, 2 s's. So s squared capital X, then we're going to subtract s times x of 0, well, that's s times 0, and then we're going to subtract x prime of 0, which is negative 1. All right, plus 2 capital X plus 4 capital Y equals 0. All right, so let's clean this equation up. We can have this as s squared plus 2 capital X plus 4 capital Y equals, okay, so minus 1 makes a plus 1. Bring it over, becomes a minus 1 again. All right, now that's equation 1. Deja vu, we're going to have the same process for equation 2. So we're going to talk about the Laplace transform. Y double prime plus Laplace transform x plus Laplace transform of 2y. Well, the 2 can come out. Equals the Laplace transform of 0. All right, so again, same thing that we did here, we'll do here. And it turns out that they have the same initial condition, so it'll look very familiar. S squared y minus s times y of 0 minus y prime of 0, so minus 1, plus capital X plus 2 times capital Y is equal to 0. Now, when we gather here, I'll put the x term first, and then we'll have an s squared plus 2 capital Y, and all that again equals a minus 1. Okay, so there we go. Our 2 equations and 2 unknowns. So, let's write those 2 equations, one right on top of the other. S squared plus 2 capital X plus 4y equals minus 1, and capital X plus s squared plus 2, capital Y, not lowercase y, capital Y equals, again, minus 1. Or, as a matrix, this can be written as s squared plus 2, 4, 1, s squared plus 2 times x, y equals minus 1, minus 1. Okay, so we're ready to actually write down what x and y are. Capital X and capital Y. I know it's really hard to keep in track. Wait, which ones are we? We're still in our algebra phase. So being in our algebra phase, we say, okay, what happens here? Well, Kramer's rule says that capital X is the ratio of 2 determinants. Now, the determinant downstairs is this original expression. So you get our s squared plus 2, 4, 1, s squared plus 2. And upstairs, well, you replace the x column by your minus 1s. So that's what we'll have. So if we do this, we're going to get minus s squared plus 2 minus negative 4, and we'll simplify that in a second. Here we get s squared plus 2 squared, and then subtract 4. So that becomes what? Well, we have upstairs, we'll have minus s squared Then minus 2 plus 4 makes it a plus 2. And downstairs, well, we'll get s squared plus 4s, s squared squared, 4s becomes s to the fourth. And then it'll be 4s squared plus 4 minus 4. So we end up, we'll write the top as 2 minus s squared, and the bottom, the 4's cancel. So let's just actually mark that really quick. Pew, pew. And we can factor actually an s squared out, so we get s squared times s squared plus 4. And that's x. Okay, good. So to finish the problem for x, we'd have to take that inverse Laplace transform, which we will, because we have to find the answer. But let's also write down what we'd have to do for y. So for y, it's very similar. Now the only difference is which column gets replaced. In this case, we'd replace the second column. So we'd have s squared plus 2, 1, minus 1, minus 1. And then downstairs we get the same exact thing. Well, look, for the downstairs, we can just skip ahead. We know what happens. We know we get s squared times s squared plus 4. How about the top? Well, we're going to get minus s squared plus 2 from our diagonal. And then we're going to subtract a negative 1. So we have a minus s squared, and then a minus 2 plus 1. Minus 2 plus 1 makes a minus 1. And downstairs, we have an s squared times s squared plus 4. All right. Whew. Okay, so at this point, we've actually done a lot of the algebra. In particular, we've solved for capital X and solved for capital Y. If you think about the process, there's like 4 steps. Step 1, take the Laplace transforms. Okay, that's what was here. Step 2, normally we would say solve for X. Here, when we're doing systems, solve for X and for Y and for whatever else you need. Okay, so that's what we've done. We're essentially at step 2. Now we go into step 3. Step 3 says, okay, rewrite this in a friendly way so that you can take the inverse Laplace transform. So that's where we're going next. And after we finish step 3, we get into step 4, which is actually do the inverse Laplace transform. All right, well, to do our next step, we need a new piece of paper. So let's go grab a new piece of paper and transfer over what we currently have. All right, so we've copied now our important parts, namely the Laplace transform version of x, the Laplace transform version of y. We need to pull these apart by partial fractions. Now for each one of them, we're going to have a similar denominator, same denominator, so it's going to be a very similar process. And so we'll get really good at it, right? And hopefully the second one will be even faster. So it doesn't really matter which one you start with, so let's start with x. So starting with x, we look at our denominator and say, well, what does it look like? Namely, we have an s squared and an s squared plus 4. Now that s squared, that's s minus 0 quantity squared. So what that's going to do is it's going to look like something over s plus something over s squared plus something s plus d over s squared plus 4. So that's the generic expression. Now the s squared plus 4, we see that cs plus d. Now the reason we break it up this way is because this s squared, it's not an irreducible quadratic, rather it's just something that's been a linear term, namely s, that's been squared. So when you have that linear term squared, you got to ladder, step your way up to the top. And so that's what we're going to end up with. Okay, so clear our denominators, right? Because that's always the process for partial fractions. So we do that. So let's multiply here. S squared times s squared plus 4. And when we do that, what will we end up with? So this one might be a little bit more subtle than things we've done in the past, so it's good to go ahead and take our time, enjoy the process. notice that when I'm choosing how to clear my denominator, I pick the term I start with. So we come to here. Now notice I only have a single s here, so I'm not going to get rid of both s's, just one of them. So I'll have as times s squared plus 4. Now here, I will get rid of two s's, so that's great. So I'll have b times s squared plus 4. And then here, I'll get rid of the s squared plus 4. So cs plus d, that's looking not very great, but that's all right. We still know what we mean, times s squared. All right. Now, is there a good choice? Well, what can we say? We can actually figure out what our choices are. There's one good choice that's pretty clear, and namely s equals 0. So plug in s equals 0, and what do we get? We'll get 2 equals gone, 4b. So you say, okay, great. B should be a half. All right, that's perfectly fine. We'll take that. B is a half. Now, the next thing we look at is say, okay, well, is there another good choice? Now, if you like to live dangerously, and who doesn't like to live dangerously once or twice, you could go with 2i. Now, I'm always hesitant to do that insofar as you get complex numbers involved and things start getting complicated. So we'll come back and we'll look at what happens if you do plug in 2i and how you can use it. So let's not do that for now. Instead, let's look at some other options that we have available because, well, we should practice. So what's our other option? Well, our other option is to look at coefficients. So imagine that we expand. And it won't be very hard to imagine because what we're going to do now is we're actually going to expand and gather. So when I say expand, think about multiplying this all out. So I have as cubed plus 4as plus bs squared plus 4b plus cs cubed plus ds squared. And now we gather our coefficients. So we say, well, what's s cubed? Well, there's an a and a c. So a plus c s cubed. Then we say, okay, what about s squared? Okay, there's a b, there's a d. So b plus d s squared. What about s? Well, there's a 4as, and that's it. Okay, great. 4as. And what about constants? Oh, there's a 4b. 4b. And now what we do is compare. Say, okay, what are the constants on the other side? So let's start with the constant coefficient. Well, that's got to match with that constant coefficient, which says this better equal 2. All right, well, that wasn't so hard. Ha, great. Well, that might look familiar. Oh, that says b equals a half. Oh, yeah, we kind of already knew that. Now here, this coefficient of s has to match the coefficient for s over here. But wait, there is no s. Well, there is. There's 0 times s. So that says 4a equals 0. Aha! A must equal 0. That's good to know. Okay, well, what about this b plus d? Well, that's got to equal what's over here. That's minus s squared. So that says that's got to equal minus 1. Now, this is a case where we know what b is. So a half plus d has to equal minus 1. So d must equal minus 3 halves. All right, no worries. Now we know d. And we come here. Say, okay, a plus c has to be the coefficient for s cubed. It has to match the coefficient for s cubed here. Well, there is no coefficient for s cubed. So this has to equal 0. Well, that says that, since A equals 0, 0 plus C equals 0, so C equals 0. Well, that was rather fast. Okay, well, that's good. So what do we have? So at this point, what we have now, catching up, we have that capital X is, well, A over S, nothing. Then we have B, which will be 1/2 times 1 over S squared. We'll come back to that in a second. And plus, we have CS, which is 0, plus D. Well, I'm just going to go ahead and pull that D out, minus 3/2, 1 over S squared plus 4. Okay. All right. Now, let's go ahead and finish this, and then I promised that we'd go back and say, well, what would have happened if we plugged in a complex thing? So, how do we handle this 1 over S squared? Well, looking at that, we say, hey, if I want an S squared, that matches this piece here. So that would be n equals 1 over S squared. Okay, that says that this will go to T. All right, so I'm going to just make a little note here underneath. This part right here will go to T. All right, great. Now, what about this 1 over S squared plus 4? Well, that looks an awful lot like the sine, but notice here, this is S squared plus 4, which is 2 squared. We need a 2 upstairs. Right now we have a 1, and of course we do what we always do in these situations, which is we put a 2 here. But if we put a 2 here, we'll need another 2 downstairs. And then this part right here, now that goes to, did I say sine or cosine? That goes to sine, yeah. That's okay. It's not a bad thing to check. All right, so what's our final answer? Well, now we know that x equals the inverse Laplace of capital X is 1/2 T minus 3/4, because 2 over 2 is 4, sine of 2t. And there we go. That's it. There's our function x. Now, we haven't solved for y. We still have to do that. You can probably guess where we're going. Another page. Yes, that is where we're going. But in the meantime, let's go back and come back to here. What would have happened if we plugged in? In this case, you would say S equals 2i. Okay, so remember, S squared, 4i squared, would be a -4. So it'd be 2 minus -4 would be 6. Let's up a little bit. Equals 0, 0. And here we would get 2c times I, because we're plugging in 2i, plus d times -4. Or we say, well, okay, that's really minus 3/2 is equal to 2ci plus d. Now the problem is, how do you finish this off? Now here is when you can actually use a little bit of knowledge to your advantage. Here's the little bit of knowledge, and of course, a little bit of knowledge is a dangerous thing. But I'm going to go ahead and tell you this because we're friends. We must be friends by now. We spent so much time together. When we look at these coefficients, all our coefficients are going to end up being real numbers. In other words, when we solve, we're going to get real numbers. So we know that C is a real number and D is a real number. What that allows us to do is to say, well, we'll take the real parts and the imaginary parts of both sides, so that this actually splits into 2 equations. So the real parts would say minus 3/2 has to equal d. And then the other thing would be the imaginary part would say, well, there's nothing imaginary on this right-hand side. There's no I. 0 has to equal 2c. And we come to the conclusion that, oh, d should be negative 3/2 and c should equal 0, which it did. So yes, it is possible to plug in complex numbers. Do I recommend it? No, because this worked out kind of nicely in this case, but you can imagine things getting a little bit more dicey. But if you do plug in complex numbers, just remember real equals real, imaginary equals imaginary, and then if you do that, you'll basically get 2 for the price of 1 is what ends up happening. Okay, well, we're only partway done. Remember, we also have to find y. We need some new space, so let's grab a new page. Okay, so once more, we know the process, so here we go. So for y, we have our original expression, minus 1 minus s squared over s squared times s squared plus 4. And we say, well, that's something over s plus something over s squared plus something s plus d over s squared plus 4. And we start from here. We clear out our denominators. So we say, all right, everything gets multiplied, s squared times s squared plus 4. And when we do that, what happens? Well, we get the following. Minus 1 minus s squared is equal to a times s squared plus 4 plus b times s squared plus 4 plus c times s plus d times s squared. Now let's go ahead and just say we're going to go ahead and embrace, expand, and group coefficients, because that's what we ended up doing last time. It worked okay, and there's a mantra, if something worked before, it should work again. I mean, that's probably true. At the very least, we should be comfortable with the process. So, all right, so expanding and then grouping, we get a plus c s cubed plus b plus d s squared. I know, you're like, Steve, isn't this like the exact same thing? Yes, because all of this is based on the denominator on the right-hand side. Our denominator was exactly the same in both x and y. So we're exactly going to get the same thing. So this is great. In some sense, it's like, oh, it's like we're recycling. Yes, it is a lot like that. Now, the thing that doesn't match is the numerator. And so now our matching things up is going to be slightly different. So for instance, for b is the constant. That has to match the constant there. So we get that this should equal -1. For a, well, that's the coefficient for s. There is no coefficient for s, so that has to equal 0. All right. We also have that b plus d. That's the coefficient for s squared. That should equal -1. And finally, we get that a plus c is the coefficient for s cubed, but there is no s cubed, so that should equal 0. Now, some of these are pretty quick. So, for instance, we see here that a has to equal 0, which then comes over here, and that says c has to equal 0, since a and c are both 0. All right, well, yeah, deja vu. Well, some things are different, though. So, for instance, we get that b will be -1/4, which is a little bit different than before. And we come over here, we see that -1/4 plus d has to equal -1. So add a fourth to both sides, and we get that d should equal -3/4. Okay. So there we go. Now we have our D. So we're ready to write up our y, and we say, hey, what do we have? We have that y is equal to a over s, 0, b over s squared. So minus 1/4, 1 over s squared. And then we'll pull out, here we have our cs plus d. Well, c is 0, d is negative 3/4, so minus 3/4, 1 over s squared plus 4. But I'm anticipating, because, we've already been through this once, and once we do something once, we learn. It says, hey, we need to put a 2 here, so we're going to put a half here, so that this part was going to go to sine of 2t, and then this part just automatically goes to t, same as before. And so our final answer for y. Okay, so y is equal inverse Laplace of our capital Y, which is minus 1/4 t, and then minus 3/8 sine of 2t. Done. Well, just so that we have them side by side, we'll just copy again the answer for x, which is a half t minus 3/4 sine of 2t. So there we go. There's the whole answer, both x and for y. I would say when you started this problem, you probably didn't think this is where we'd end up, but we did. There are things you can check. For instance, how about the initial conditions? They had to be the case when you plugged in 0, you got 0. Well, yeah, everything goes to 0. Well, what about the derivatives? Well, you'd have minus 1/4. Here, you'd have minus 3/8 times 2, which is minus 3/4. Then you end up with the cosine. So minus 1/4 minus 3/4 cosine 2t, plug in 0, you get minus 1/4 minus 3/4, which is minus 1, which is good. That's our initial condition. Here, you have a half, and then when you come here, you have minus 3/2 cosine 2t, plug in 0, a half minus 3/2 is minus 1. Again, our initial condition. So, woohoo! It works. And indeed, if you go through and you plug it all in, it all works out. It's amazing. It's cool. Is it better? I don't know. In some sense, it's just a different way of approaching problems. And we're still learning. So, all right. We made it all the way. All right. Thank you for sticking around. And, well, keep practicing. It'll become more natural the more you practice. All right. See you again.